So what should the leading order effective theory do? What should we demand of it? We've basically now set up all the things that we need to think about in order to figure out what the leading order effective theory is. So let's do that. OK, so what do we demand of this Lagrangian? It should yield the propagator, of course, and also interactions. And it has interactions both within this effective theory. It has interactions both with collinear gluons, from that diagram over there, and with ultrasoft gluons. And you can see even from here why we need two different fields, because there has to be some way of telling that we have a different propagator in this case than in that case. Or put another way, the external field here has a different power counting than the external field here. So this already we're kind of seeing that we need two different gluon fields in this effective theory, as we said earlier. So the Lagrangian has to have interactions with both of them. It has to have both quarks and antiquarks, because remember that collinear quarks and collinear antiquarks both existed as leading order things. It's not like HQET where one of them gets integrated out. And basically that is just the statement that say you have a collinear gluon going along very quickly, it can pair create two collinear, a quark and an antiquark. And if they're, again, collinear, that's something that has to be allowed to happen at order 1 in this effective theory. OK, so far so good. This is just saying what are we going to be able to, what kind of fields are we going to have in this Lagrangian. This third bullet is related to what I was just stressing, that we have to get a leading order propagator in different situations. So somehow the effective theory has to know something about the size of momenta that are running through it. And if we want to be strict about defining the effective theory and defining the leading order term, it's not OK that we expand later. We really have to expand ahead of time. And so whatever the Lagrangian is, it should just give this, and it should just give this, and it should not give these dots. OK? So that's what I mean by not having no additional expansion. And the final thing is a little more subtle, and that is that we should think ahead. So when we design this effective theory, we're not only going to want to describe the leading order term, but we're also going to want to describe power corrections. Because if we can't describe the power corrections, we don't really have an effective field theory. So whatever we do, we should make sure that we have a notion of what's going on with higher order terms, that they're well-defined things, that we can think ahead about what the operators are going to look like. And we need that in order to know that we can formulate those operators and make sure they're suppressed. So another way of putting it is that we should set things up so we don't have to reset things up when we start talking about power corrections. So we really should think about the effective theory globally, even though we're sort of starting by formulating the leading order term. We should think about the power corrections as well and how those interactions are going to behave. OK, so that's saying that we want to think about at least what these dots are going to look like, what this plus dot 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 is going to look like. OK, so this is our goal, and we'll go through it slowly. So let's start with, this is a top-down effective theory. So we can start with QCD, and then we can integrate out the off-shell degrees of freedom, we can just formulate from what the SCET is by starting with the QCD Lagrangian and splitting it into the fields that we want and manipulating it. So let's start with psi bar ID slash psi. And let's write psi in terms of two fields. And this goes back to our discussion when we were talking about spinors. So these two fields have a projector on the full theory field, and they obey n bar slash n slash n slash n bar slash Cn is Cn, and n bar slash n slash phi n bar is phi n bar. So I want to write out the QCD Lagrangian in terms of components, because the different derivatives, the different components of the covariant derivative and the different regular derivatives inside that derivative have different power counting. OK? So let's do that. And I'll introduce these two fields in order to do that. So if you like, I'm just taking QCD and writing it in these coordinates that we're saying are useful coordinates for talking about SCET. So decompose the d slash and just write out the fields as these two pieces. And then I can multiply these out, and because of the projection relation, some of these products will vanish. So if I only write the pieces that don't vanish, then I only have 4 pieces, which are these 4. OK, so all other combinations that I didn't write vanish, and those 4 survive. We'll do one example so you see what the strategy is for getting rid of the other terms. So let's consider one of the other terms. Let's consider the guy with the d perp slash, but between 2 Cn fields. So I can insert the projector. And then I can move it through the d perp slash. I'm moving 2 things through, and they both have 0 dot product with d perp, so there's no additional terms. I just can push it through. And n slash on Cn bar is 0. So n slash on Cn was 0, remember. And if you take the dagger and make it into a barred relation, you also have this formula. So this is 0. And a similar thing, by inserting projectors, we can figure out which terms are non-zero. And these ones I'm writing are the non-zero ones. This guy's 0, that's why I didn't write it. OK, so any questions so far? Hot today. Drink lots of water. OK, this is just QCD. I haven't done anything. I just wrote QCD out in some strange coordinates. So now I'm going to do one thing, which is going to end up simplifying our lives a little bit later on. And I'm going to use the fact that when we talked about production of quarks, we said we're going to produce this Cn type of quark and not the phi n bar type of quark. So phi n bar, remember, corresponded to subleading spinor components. So let's just decree that I don't really care about this field, and therefore I don't need to have any current in my path integral that I couple to this guy. So it's like an auxiliary field, if you like. And because the path integral in this fermionic field is quadratic, we can just remove it from the path, just do the path integral over it. Once we know that there's no source term for it, we can just do the path integral, since all the terms are explicitly written over there. So let's see what happens when we do that. So doing the path integral for this quadratic field just means solving the equations of motion. So we take the variational derivative with respect to phi n bar of the Lagrangian, and that gives us the following equation. We could multiply both sides of this field by both terms in this equation by an n bar slash over 2. And then we can use the projection relation. Just to simplify the Dirac structure a little, we can move the Dirac structure from here to here. And then we could formally solve this equation for the phi n bar. It's an inverse covariant derivative. And if I can push this through this at the cost of a sign, so if I move it to the right-hand side of the equation, that takes care of that sign. So I did two sign changes. I moved something to the right, and then I pushed these through each other to get that equation. OK, so what this is saying in terms of the original field is that I have this equation for psi. So if we take that result and we plug it back into our Lagrangian, which I meant to give a star, then we'll just have the equation in terms of this C. We already used two terms. And so those two terms, when we plug it back in, they just cancel. So there was two terms in the Lagrangian that had psi and bar, and the remaining two You have that. Okay, so this is Lagrangian. It's just in terms of the CN field. We'll call it double star. This was supposed to be, previous guy was supposed to be star. Okay, so several questions arise. What have we done? Do we like this inverse covariant derivative? Are we happy with that? Are we unhappy with it? So what does an inverse covariant derivative mean? Well, actually, just what does an inverse derivative mean? This is an inverse operator. So what does that mean? So the way you define an inverse operator is exactly how you define an inverse operator in quantum mechanics. So let me remind you of that. This is the analog of, in quantum mechanics, having, say, a 1 over r potential. But if r is an operator, then you have a 1 over an operator. And the way that you define that is by the eigenvalues. So 1 over I n bar dot partial of some field, phi of x. You can write it out in terms of momentum space. And so if we go over to momentum space, that's the eigenbasis. And then the eigenvalue is just 1 over the momentum. This component of the momentum. Okay, so it's just the Fourier transform of that. So this is encoding. Yep.
Yeah, I have a question about whether or not you have actually done nothing.
I have done nothing, yeah.
Yeah, it seems like it.
So that's my next comment.
Right. And so phi n bar
Yeah, so
actually corresponding to submitting spinner would mean that you're only considering
right.
interactions that are all collinear, and the original QC Lagrangian does contain
Yeah.
interactions.
So the only difference between what I've done so far and QCD is that in QCD we'd have a current. If we were to think about QCD, we'd couple external currents both to this phi n bar as well as the Cn. And that's the only difference. But people actually, there's a small community of people that actually think about this Lagrangian as the QCD Lagrangian. And that's because if I was willing to couple a current to this particular combination of fields, I could still call it QCD. Okay, so in that sense, if I really demand that I'm only producing CNs and I just have a term that's like J CN, and I don't have this phi n bar, then it's something different because I'm not directly able to produce these guys. But if I allow myself also to couple to this combination here, then I can do everything in terms of these CN fields and really just QCD.
So star is exactly equal to QCD if you're only producing in
exactly.
the direction or something?
No, just even simpler. It's exactly QCD if I only produce these CN. If I just say I am only interested in operators that produce this particular spin component.
I'm trying to say that it's like
yeah.
physical.
No, I haven't made any expansion to make it collinear yet.
But if there was a hard scattering with two like totally different directions,
yeah.
well, you could produce phi n bars, right?
Yeah, but that would be another Lagrangian. So this Lagrangian is only producing, this Lagrangian in the end will only be useful for producing particles in the n collinear direction. That's what I'm going to be after. And I'd have another copy of this. For each collinear direction, I have one additional copy of what I'm doing now.
Right, so you've lost the ability to produce like hard scattering by doing this. But
by just doing this.
Talk about that, it's totally
right. That's right. Okay. So we're far from done. And really, this is just sort of a warm-up. Really, what we've done here is we've just written things out in terms of components. And it's true that these derivatives here have different power counting. And we're going to make use of that in a second. And we've also just sort of focused our attention on this guy that we could produce at leading order from a hard scattering in some particular direction, such as in our BDU example. So if we're interested in just one collinear direction, then there's two components of the spinner that are always the big components, and we focused on a field that gives those components directly. So what do we have to do still? So there's 3 more steps. So we have to separate collinear. So far, we just have one type of covariant derivative. We have to separate out the fields that are in that covariant derivative, in particular the ultrasoft and collinear gauge fields have to be separated out. Another thing we have to do is we have to separate the collinear and ultrasoft momenta. There's 2 different types of momenta, as we saw in this simple example of a gluon momenta flowing into a propagator, and we actually have to distinguish them. And then we have to expand. So until we do these first 2 steps, there's not really anything to expand. And so once we've distinguished those, we'll be able to say that certain things are larger than others. And then we'll be able to figure out what the leading order Lagrangian actually is.